So we're going to talk about the kinetic molecular theory again, and to look at how it affects pressure and volume and pressure and temperature. So we want to keep these in mind, our 5 postulates or assumptions: that the volume of the gas is small, there's no forces between molecules, and they're in constant motion and always traveling in a straight line. Collisions are elastic, and the kinetic energy is proportional or equal to 1/2 mv squared, and it's proportional to temperature. We want to keep all those in our head. We want to do a thought experiment, and they've done real experiments like this, where we put a gas in a piston, and I'll talk about this in other learning objectives also. And here's our movable piston. We put a pin here. And so what happens is these molecules are moving in random directions all over the place. And they're colliding with each other. There's so many collisions a second you can't even begin to talk about it. And this piston can slide up and down, but the gas is holding it up by colliding with the piston. And that keeps it up against this pin. Okay? And so we will have a pressure due to collisions of the gas with the piston and with itself and with the walls. And this will have a volume that is the volume of the container. So that's our picture of a gas right now. Now we're going to take the same gas with the same number of gas molecules in it. There they are. And I'm going to decrease the volume. The volume decreases. So what happens to the number of collisions of our gas in here? The number of collisions should increase, and therefore, because the collisions are exerting pressure on the walls and on the piston here, we're going to see more collisions, therefore higher pressure. So what we see then, if we plot the volume is large, if we plot volume versus pressure, way out here, at a very large volume, the pressure is very small. As we come in and decrease the volume, we see the pressure start to increase, okay? And you get this standard curve that I can't draw very well, but looks like that, all right? And so this is what the kinetic molecular theory has to do with pressure and volume. And this is in the next one, and it'll be called Boyle's Law. P1 V1 equal P2 V2, and I will go over that in the next learning objectives. Now let's think about volume. Let's plot volume versus temperature. So now we're going to take our piston, fill it up with gas. There it is. And we're going to not put a pin in here at all. There's no pin this time, which I'm drawing in. Right here, we're going to remove that pin, and so this piston is free to move up and down. What happens if we increase the temperature? If we increase the temperature, that means we increase the kinetic energy, which means we increase the velocity. So we're going to have molecules moving faster, which means they're going to hit more hard. They're going to have a harder collision, more momentum transferred. If you know anything about physics, you don't need to worry about it. Just think about a baseball hitting you moving slow or fast. But they're going to have harder collisions, and we're going to have more of them because they're moving faster. And so what happens to this? The volume increases. We have more collisions in here, and so the number of molecules don't change, but the volume increases. And so we see something that runs like this: volume versus temperature, nice straight line. Okay, so let's talk a little bit about where the kinetic molecular theory fails, and the problems we run into. So at very high pressures, so if I just keep pushing this down farther and farther and farther, the volume gets smaller and the pressure increases. Remember, our graph looks like this. Volume gets smaller, pressure increases. Pressure, volume. And so at a very small volume, what happens is the volume of the gas molecules start to become important. And this is, so it's small volume and high P, high pressure. The volume of the gas is no longer zero. It starts to take up space because there's so many molecules crammed into a small space. That's one violation of the kinetic molecular theory, one problem it has. So we've just talked about one place where the kinetic molecular theory will fail, and that is up here with where the volume is small. And now we're going to talk about the second one where there are no attractive forces between molecules. That's also wrong. There are attractive forces. They're just very, very small. And the only time this is going to become important is when you have the gas moving very, very slow. The place where the gas motion becomes very, very small is when the temperature is small. So temperature is small, then kinetic energy is small, and the velocity is small. And this happens at extremely low temperatures. So at low temperatures, the attraction force between two molecules, these attraction forces start to become important. And eventually, at low enough temperature, you get condensation. And this is the point at which the attraction forces overcome the repulsion and overcome the velocity. So condensation at very low temperatures. And the gas is no longer considered, it's no longer considered a gas or even an ideal gas. So at low temperatures, the intermolecular forces, the attraction forces in the molecules become important.